Hello everyone, welcome to today's video on the topic interaction of electromagnetic radiation with the atmosphere. In this particular lecture, we will be talking about how EMR interacts with the various constituents of the atmosphere and its influence on remote sensing that we do. In the last lecture, we saw that whenever a medium through which EMR is travelling is actually a lossy medium, then the EMR will undergo scattering and absorption. That is, the total energy of EMR will be reduced by these two processes, and same two processes will happen in the atmosphere. Atmosphere contains several gases, dust particles, aerosols and other constituents which will interact with the electromagnetic radiation, which will reduce its final intensity. So, as I said, atmosphere will interact with electromagnetic radiation through scattering and absorption. How scattering will occur? Scattering will occur because of presence of tiny gas molecules or aerosol particles. Aerosol means some sort of dust may be present, like wind may be blowing carrying some dust particles, or like when people burn stubble, it will create dust, all these things. These are called aerosols basically. So, when aerosols are present, when gas molecules itself, or when rain drops, ice particles, etc., when these things are present in the atmosphere, they cause scattering. Similarly, the gas molecules present in the atmosphere such as CO2, water vapor, etc., will absorb some amount of radiation for changing its nature to some extent. So, energy will be both absorbed as well as scattered. First, we will see about scattering in the atmosphere. The scattering of EMR in the atmosphere can be classified into three types: Rayleigh scattering, Mie scattering and non-selective scattering. So, those three are listed here in this slide: Rayleigh, Mie and non-selective, the three types of scattering that occurs in the atmosphere. As we have already studied, scattering reduces the amount of useful energy, that is, say light ray is coming in this particular direction, the presence of gas molecules or dust here will scatter this radiation in different direction, and if we are placing some sensor here, the net energy coming in the direction will be reduced. So, scattering reduces the amount of useful energy in the given intended direction and also introduces some unwanted radiation in the image. Unwanted radiation in the sense, say here radiation is scattered in different directions. After some time, this scattered radiation also will reach the surface through different means or with different intensities. So, basically scattering at one hand reduces the amount of energy coming in the particular direction. On the other hand, it adds some component of scattered energy, like all points on the earth's surface will receive some energy in addition to sun's direct energy. This additional energy is actually coming in from the radiation that is left in the atmosphere itself through scattering. So, what are these three types of scattering? First, we will start with Rayleigh scattering. Rayleigh scattering is also known as molecular scattering. As the name suggests, this scattering occurs due to tiny gas molecules present within the atmosphere. The molecules, when the size of the molecules is too small is much less than 10 times of the wavelength involved. That is, say if the wavelength of the electromagnetic radiation, let us say it is around 0.5 micrometer. If the molecule size is much less than say 0.5, like 1/10 of the molecules or 1/10 of the incoming EMR, then this particular EMR will undergo Rayleigh scattering. So, Rayleigh scattering will happen when the molecules has a size much smaller than the wavelength that is coming and interacting with the molecule. And this Rayleigh scattering varies inversely with the fourth power of wavelength, that is, the amount of scattering will be proportional to 1 by lambda power 4. That is, as the lambda becomes smaller and smaller, the amount of scattering will be keep on increasing. If we take visible light, so visible light consists of 3 colors, primary colors, blue, green and red, 0.4 to 0.5 micrometers, 0.5 to 0.6 micrometers and 0.6 to 0.7 micrometers. This is the wavelength range of these 3 primary colors as we know. And we normally see the sky in bright blue color if the sky is really clear without any sort of like lot of clouds and dust particles around, we see the sky as blue in color. This is primarily because of Rayleigh scattering. I just listed the wavelength of 3 primary colors, blue, green and red. Among these 3, which our eyes can see, blue has the shortest wavelength. So, the amount of scattering that blue undergoes is much higher than the amount of scattering that green or red will undergo. Hence, what will happen when the sunlight enters the atmosphere carrying blue, green and red, blue will be scattered to a larger extent in the top of the atmosphere itself. Only the remaining portion will reach us. So, the blue is now scattered all along the atmosphere itself, it is not reaching the earth's surface. That is why we see the sky as blue in color, blue is now scattered entirely on the atmosphere. Similarly, during evening time like sunset and sunrise time, we will be seeing the sky as bright red in color. This is because whenever during morning or evening the sun will be at the horizon, the distance between or the distance through which the light has to travel is much more than during daytime. Like I will give a small example here, like say this is the land surface, this is like let us put an hemisphere around the land surface, some observer is standing here. If the sunlight is overhead, if the sun is overhead, the distance the light has to travel is much less. On the other hand, if the sun is at horizon, the distance light should travel is much longer. So, as the distance through which the light travels increases, amount of scattering also will increase, because as the distance becomes larger and larger, the interaction will be increasing, and as interaction increases, scattering and absorption will be more basically. So, due to this increased path length, what will happen? First blue will be scattered and it will be left in the atmosphere itself, then green and red will be passing through. Even green will be scattered because of this longer path length, green also will be scattered completely, only red will escape the scattering because of its longer wavelength and it will reach our eyes. That is the reason we see the morning and evening sky as red in color. So, Rayleigh scattering is the primary reason for these color appearances, and the amount of Rayleigh scattering varies with respect to 4th power of wavelength. Yeah, as I said before, here in this slide I am just explaining the amount of scattered light, the intensity of scattered light is much higher at shorter wavelengths and it is much lower at longer wavelengths. So, the main problem of Rayleigh scattering for remote sensing is it introduces haze in the imagery. Haze means the image will be unclear, it will have like some sort of like a dusty appearance, it will reduce the contrast in the imagery. The haze effect will reduce the contrast in the image. So, we will see about like the reduction in contrast, what effect it has and all briefly in some other lectures later in the course. Next we are going to see about mice scattering. Mice scattering is also known as aerosol scattering or dust non-molecular scattering. So, this type of scattering occurs when the size of the molecule is 0.1 times to 10 times the wavelength involved. So, here there is like a lower bound and upper bound of size of the molecule. So, here the size of the molecule will vary from 0.1 times to 10 times the wavelength involved. Then these sort of molecules will actually cause mice scattering. Mostly the presence of dust in the atmosphere causes mice scattering. Whenever dust is present or some aerosol particles is present, we see lot of disturbance in our vision, that is basically due to mice scattering. And mice scattering, the intensity of scatter will be much higher than Rayleigh scattering. So, the intensity with which mice scattering will occur will be larger, like whenever there is a dust storm passing through before our eyes, we will not be able to see anything because of like lot of blockage will be there, lot of energy will be scattered. So, the amount of scattering will be much higher in mice scattering. Then the final type of scattering is called non-selective scattering. Non-selective scattering, some textbooks treat it as an extension of Mie scattering also. Like non-selective scattering will happen when the size of the molecule involved is more than 10 times the wavelength involved, like the molecules is much bigger in comparison to the wavelength involved. And non-selective scattering, as the name suggests, will scatter all the wavelengths equally, like it will not have any sort of wavelength dependence, it will scatter all wavelengths equally. So, what are the primary causes, primary materials that causes non-selective scattering? Larger particles such as ice crystals in cloud or water droplets, such things which are much bigger than the wavelength of EMR will cause non-selective scattering. One important or interesting point to notice, the main reason for clouds to look white is non-selective scattering. That is, clouds, if you look at, primarily composed of water vapor, water droplets, and some clouds ice crystals also will be there. So, all these things, water droplets and ice crystals and all will scatter all the incoming radiation equally. Non-selective scatter will happen, all the radiation will be equally scattered. Because of this, we see clouds as white in color. Why white in color? All wavelengths will be scattered equally in all directions, and the primary colors that we see as red, green, blue. When these three things mix equally, we perceive it as white in color. So, since all the wavelengths that is coming in are scattered equally, when our eyes see it, we will see a equal mixture of red, green and blue, and we see clouds as white in color. So, just to do like a summary of scattering. So, scattering is 3 types: Rayleigh, Mie or non-selective. The primary particles that causes Rayleigh scattering as gas molecules. For Mie scattering it is the dust or smoke, and for non-selective scattering it is water vapor, ice crystals, etc. Rayleigh scattering varies with wavelength. Non-selective scattering and Mie scattering are relatively non-dependent on wavelength, especially non-selective scattering. And if you look at the atmosphere levels, the different layers of atmosphere, like here from the surface and up to 20 kilometers is given in this particular figure. So, when the electromagnetic radiation from the sun is coming in, the top portion of atmosphere is consists primarily of like gas molecules. So, most of the Rayleigh type of scattering will occur in the top portion of the atmosphere, like when it is coming in, say here like about 8 kilometers above the surface, the atmosphere will be containing lot of gas molecules, hence Rayleigh scattering will be happening. Once it comes very close to the surface, within like last 2 to 3 kilometers within the surface, the EMR will encounter water particles, dust particles and everything, which will cause Mie scattering and non-selective scattering. So, Rayleigh scattering happens relatively higher up in the atmosphere, and Mie scattering happens relatively lower to the surface, much closer to the surface. Okay. So, one more interesting fact is I wanted to tell you is the red color we use widely in signal to indicate danger or stop sign is because red is scattered the least. When we compare the 3 primary colors, we can see blue, green and red. Red is scattered the least among these 3 colors. Whatever the scattering happens, red will encounter the smallest amount of scattering, due to which red wavelengths can travel for longer distances. Because of this particular reason, people have chosen red to indicate danger sign. So, that say if someone is traveling in a vehicle, red light will appear from a much longer distance itself. So, they will see the red light from at a longer distance, they will start the process of braking. In order to give a clear indication to the user, red is being used as a sign for danger or stop signal. Next we are going to see is the absorption of EMR by Earth's atmosphere. So, as I said before, atmosphere consists of lot of gas molecules, O2 molecules, that is oxygen molecules, water vapor, carbon dioxide, ozone, many materials are there. Due to the presence of such materials, each of them will interact with electromagnetic radiation and they will absorb certain portion of EMR. So, in this particular figure in the slide I have presented how EMR is transmitted and how the transmission varies with wavelength. So, transmission is, say if some amount of energy is coming in, say some 100 units of energy is coming in, let us assume 20% of energy is absorbed. So, we call transmittance as 80% or 0.8 as a fraction. So, what is the amount of energy that is left after absorption, we call it as transmission. So, transmission is given here in this percentage. We can see from this particular figure that the transmission of the atmosphere varies a lot with wavelength. At smaller wavelengths like less than 0.4, which we call it as the ultraviolet region, the transmission of the atmosphere is very low, like the transmission is less than like 5% or 10%. Atmosphere is almost opaque to UV radiation. This is because of the presence of ozone in the atmosphere. So, the ozone absorbs almost all the UV radiation incident on it, thereby saving the living organisms on the earth surface from the harmful nature of UV radiation. So, ozone effectively absorbs almost all of UV radiation. After UV part, if we come to the visible portion of the spectrum, we can see that the transmission is relatively higher, like after you cross this particular portion. After you cross this particular portion, the transmissivity is bit high, not bit high, actually very high, it is in the range of like 80 to 90%. So, this is in the visible part. So, 0.4 to 0.7 micrometers. Still here we are having like a very good transmissivity in the atmosphere. So, that is why we will be getting most of the visible energy from the sun without much hindrance. Atmospheric absorption is much lower in the visible portion. After the visible portion, after 0.7 micrometers and all, there are like some very sharp absorption features. Here there is absorption feature, here around like 1.3 or 1.4 micrometers, that is a very strong absorption feature, something like that. So, atmosphere presents a characteristic dips in different portions. So, wherever there is like atmospheric transmission is very low, we call such portion as absorption bands. Say for example, around like 1.3 to 1.4 micrometers, there is a very strong absorption band, the transmission is very low or the absorption is very high. This we call it as an absorption band. Similarly, around 1.9 micrometers, there is a very high absorption band in the atmosphere. So, such energy coming in 1.3 to 1.4 micrometers or 1.9 micrometer wavelength, those energies will not even reach the earth's surface from the sun. So, whenever sunlight is coming through the atmosphere, these particular wavelengths which are highly absorbed by the atmosphere will not reach the earth's surface, they will be stopped completely in the atmosphere itself. So, again we go back to this figure. So, here in this figure you can see after like around like 3.5 or 4 micrometers, atmosphere is fairly opaque in the sense transmittivity is very low, and after say 15 micrometers or something, there is like a huge gap, like the transmissivity is extremely low. Then when we enter the microwave portion of the spectrum, the transmission suddenly goes up, like after like 1 centimeter wavelength, when we enter the microwave portion, we can see the transmission of the atmosphere is fairly high. So, atmosphere is transparent to microwave wavelengths. So, microwave essentially is free from atmospheric absorption. So, the amount of absorption that is undergone by microwave is extremely low because atmosphere is fairly clear. On the other hand, if we come to shorter wavelengths such as like visible IR or MWR portions, there are characteristic bands at which the atmosphere of molecules will absorb radiation. Such characteristic bands are called absorption bands, and the energy contained within such absorption bands will not reach the earth's surface, it will be absorbed completely in the atmosphere. So, this particular slide is actually like a mirror image of the past slide. In the past slide I showed you atmospheric transmission, here I am showing you atmospheric absorption because of the different gas molecules that is present. Say here the atmospheric absorption is now divided into its constituent components which causes atmospheric absorption at which wavelength. So, this is the total effect of all particles or all molecules together, and these first 4 figures are due to the individual molecular components. Say for example, N2O, nitrous oxide, is the main reason for absorption in the mid-wave infrared wavelength around like 4 micrometers. Oxygen and ozone, O2 and O3. O3 is the primary reason for absorption in shorter wavelength or UV radiation. Oxygen is the primary absorption in around like 0.6 micrometers. Similarly, CO2 is a very strong absorber of around like 2 to 3 micrometers here. H2O is the primary cause of lot of small atmospheric absorption windows around like say 1 micrometer, just 1.3 micrometers, 1.9 micrometers is a very strong water vapor absorption band. Similarly, between 2 to 3 micrometers, all such bands are absorbed due to H2O. So, each molecule absorbs different portion of wavelengths, and since atmosphere is a mix of all these molecules, the final effect that we see is a collective one of all these gases, that is given in the last portion of the slide. So, if you look here around like say for example, we take the visible portion around 0.4 to say 0.7 micrometers, the absorption is very low and we can receive that particular wavelength in earth's surface. So, such portions where the atmosphere is fairly transparent and allows us the EMR to enter the atmosphere and reach the earth's surface are known as atmospheric windows. So, the atmospheric windows are the wavelength bands at which EMR will reach the earth's surface. In atmospheric absorption bands, EMR will be stopped in the atmosphere itself. In atmospheric windows, EMR will be allowed to reach the earth's surface by the atmosphere. Hence, if we want to practice or if we want to do remote sensing of earth's surface, then essentially we should design sensors which should be able to sense the energy in these atmospheric windows. We cannot put sensors in the atmospheric absorption bands if we want to see the earth's surface. So, this is again the absorption with respect to wavelength given in this particular slide. One interesting question I wanted to ask is, some remote sensing systems consist of bands that are located in atmospheric absorption bands. Can you guess why? Please take few seconds, please pause the video and think over it. The main reason for putting some bands that are like centered around this atmospheric absorption bands is to get more information about the atmosphere itself. So, such absorption bands helps us to know more about the atmosphere, like how much CO2 absorption is occurring will help us to model the presence of CO2 content. Similarly, the presence of water vapor will help us to monitor water vapor movement. Water vapor movement is essentially like the primary reason for rainfall in different places. So, for remote sensing of atmosphere, it is quite natural to put few bands in centered around in this atmospheric absorption bands. Before we close down, I just want to put one more question to you. We discussed about atmospheric scattering and atmospheric absorption. Just related to that, this question will be there. The question is there in this particular slide. So, the shadows that we see are not completely dark and we can see objects within shadows, like this is like a tall building and its shadow is falling on the ground, still we can see whatever is there in the shadow. Similarly, here also some objects, even though not clearly visible, something is visible. So, why the shadows are not completely dark? What is the energy that is falling on those objects? Please pause the video and think for a few seconds before knowing the answer. So, the answer for the question I posed is scattering, the light scattering present in the atmosphere is the primary reason for irradiating the objects within the shadows. That is, I said before, like whenever there is a land surface, like sun's direct radiation will be coming in. This will be scattered all along the atmosphere, and after some time this scattered radiation will come and fall down. Say for example, we have like a building here, okay. So, like I draw here again. So, there is a building here and sun is giving its energy. So, this building will cast a shadow here and this portion will not receive sun's energy. At the same time, the scattered light present all across the atmosphere will be falling on the objects within the shadow portion, and that is why we are able to see objects within the shadows. So, this sort of scattered radiation that is falling on an object, we call it as diffuse radiation or diffuse skylight. That is the sun's radiation, the direct radiation from the sun, we call it as direct sunlight, and the energy that earth surface receives because of the scattered radiation, we call it as diffuse radiation or diffuse skylight. Because of the presence of diffuse radiation or diffuse skylight, we are able to see objects within the shadows. So, just to summarize what we have learnt in this particular lecture is, we have learnt about scattering and absorption taking place within the atmosphere. Scattering is divided into Rayleigh, Mie and non-selective scattering. Scattering essentially removes the energy in one particular direction and redistributes it in several directions. So, scattering is will remove some energy and also will add some energy again in form of diffuse skylight. Similarly, absorption is will remove the energy completely. So, such those wavelengths which are completely absorbed by atmosphere will not be useful for remote sensing of earth surface. For remote sensing of earth surface, we need to design bands such that they fall in atmospheric windows, that is where the atmosphere is fairly transparent. With this we end this lecture. Thank you very much.